So what we're looking at today is interval and set notation. So a set is just a group or a collection of objects. Braces are used to list the set members. So if we had a set of 1, 2, 3, we would use a bracket and then list out the numbers. So one we could do is 1, 2, 3. So we can list it out like this here. Now doing this is good and helpful as long as the list is not overly big, because if it gets too large, it's going to be hard to list them all. Because if we were wanting to, say, list down a set of the numbers between 1 and 1,000, that would take a lot of space to try to write out, because we'd have to write each individual item, each individual element, from 1 to 2 to 3 to 4, going on and on and on. So sets, writing them this way is nice if we have a small amount, but if we have a bigger amount, it's not as useful. And we also have set builder notation. It's used to define the set in terms of the properties of its members. We got these here. Now, set builder notation normally has a kind of a setup to it. And when we talk about set builder notation, the main property that it's going to have is that we're going to, let's back up. There we go. Okay. Set builder notation. Normally, set builder notation is going to be X such that, and then we're going to have some property that we're going to fill in. Normally, what's going to come after X is going to be this little e, which is determined to be element. X is an element of some type of number or group of numbers. And then we can identify it or attach some properties to it. So we could say X is a real number such that X is greater than 2. So we're talking about all the numbers greater than 2. So this here is a little bit easier way to write a set of numbers if we're talking more general or bigger groups of numbers. So any questions so far about set and set builder notation? And we'll look at these as we go through. Now with sets, we also have subsets. And a subset is a set of a larger part. And really the main thing about subsets is everything that's in a subset is also in the set. Is when all of the members of set A are also in set B. So we could say A is a subset of B because everything in A is contained in B. But we can't say that B is a subset of A because what? Because here A has 1, 3, 15, 27, 20. So B has 1, 3, 15, 27, 20. Everything in A is contained in B, yes? Can I say that B is a subset of A? Why not? Yes, because B has more elements than A. Because all the elements in B are not in A, it can't be a subset. So a subset is just a smaller group of the whole. Just like this classroom here is a subset of the entire high school because it contains part of the high school but not everything. Now a subset could be everything. There's what are we missing? 2, 11. Because if we add 2, 11, I think 100. Yep. Now they're subsets of each other. So just because they contain everything doesn't mean they're not subsets. A subset can be itself. So another example is A has the elements A and B has A, B, C, D. So A is still a subset of B. as long as it has all the elements in one, or some of them, it can be a subset. So questions on this here so far? We pretty good with subsets? Yes? So let's look at what we're going to do here is we're going to look at writing subsets. Now, when we look at this here, 4 and 5, well, a subset of this could be a set containing the element 4. Because the set containing the element 4 is a part of the set, is a subset. Another subset would be what? 5, the set containing 5. Because both of these are subsets of the set 4, 5. And last but not least, our other subset is 4, 5. So we can have the one that contains both 4 and 5. So we have 3 subsets for this here. So for the set 4, 5, we can have the subset 4, the subset 5, and the subset 4, 5. Any questions on this so far? So let's look at B. Can anybody give me a subset of CD? The set containing C. What's another one? D. And CD. And that's it. Now, if we wanted to get particular, we could add another one, but that was saying that order matters. If we said that order matters, then this pairing 5, 4 would be different than 4, 5. But for the most part, when we look at this here in sets and subsets, order doesn't matter, so we wouldn't include this one here. So when we have 2 numbers, we get 3. 3 different subsets. We're good with these here. Yes? Well, let's look at a set with 3. So what's one of ours? So we have the set containing 2 would be 1. Set containing 4. And 6. So we can have each one of the different elements as a subset. Then what can we have? So we'll do, 2, 4, 6 will be the last one we can do. But we can also have the set 2, 4, because it's still a subset, yes? What's another one? We can do 2, 2, 6. 4, 6. Why wouldn't I do 4, 2? Yeah, it's just a different order because we already have 2, 4. So 4, 2 wouldn't add anything. So that there's all the subsets we could have for 1 with 3. So that increased a little bit, didn't it? Because when we had 2, we only really came up with 3 subsets. We go to 3, 1, 2, 3, 4, 5, 6, 7. It increased a decent bit. Are we good with this one here? Because I'm going to have to erase. We good with these? We good, Stephanie? Okay. So when we look at this one here, well, one of the elements we know for sure is E, F, G, and so each one of these can be a subset. What else can we have? Yeah. Then what? I'm going to stick with E first, and then I stick with the first one. I always start with the right and move out. That way I keep them in order. So I know what I have. Because EFG, EF, EG, EH. We don't do FE because we already have it, but we have FG, yes? And then what would we have? F. Are we done with F? Yep. And then we have GH. So these are the kind of subsets we've had up to this point, yes? What's the next one we could have? EFG. And then what? Yes. One, two, three, four, five, 6, 7, 8, 9, 10, 11, 12, 13. Okay? We got two more. F, G, H. And last but not least, and that's all of them. So when we had 3 elements, we ended up with 7 subsets. When we have 4, we go to 15. These increase fast, yes? Because the number of subsets is increasing as we go about this. Any questions on subsets? Are we good with subsets? And the reason they say write all the non-empty subsets is because writing empty subsets can actually get kind of redundant. We can add infinitely many of those. And a empty subset is written like this here. There's a 0 with a line through it means the empty set. There's nothing there. Because realistically, when we talk about sets, 0 is a number in the set. It is a part of the set. So we can't say something is empty or not there with 0 until we do 0 with a line through it. So this here is the empty set. And what's a subset of the empty set? Well, I could have the set containing the set of the empty set is a subset of the empty set. But I can also say that the set containing the set containing the set of the empty set is a subset of the set containing the set of the empty set. So we can infinitesimally keep going out with the empty sets. But that's most of the reason why when we talk about subsets, we're looking at the non-empty subsets because they can go on indefinitely. Yeah. Number types. Probably at some point you've gone over the different types of numbers. So I'd give yourself some room because there are several different types of numbers. And the first type is natural numbers. Natural numbers are something that we can count, so 1, 2, 3, 4, 5, 6 going on. Natural numbers are naturally the numbers you count on your hands and your feet. So we can count up. Now they don't include 0. They don't include 0. There's no decimals, fractions. It's just going on forward. Now I'm going to do this on the board. I'll just show you visually kind of what this does. And we keep going on from there. So natural numbers give us these numbers going from 1 out, and they just increase. And that's our natural numbers. Now the natural numbers do have a symbol. It's an N with 2 lines. So in mathematics, when you see this thing here, they're talking about the natural numbers. It's just a symbol to represent them. So we go with natural numbers. Yes? After natural numbers is something called whole numbers. Now, the only thing that whole numbers adds is 0. Natural. Whole. Now, whole numbers really doesn't have a symbol. It'll sometimes, I'll denote it as a W with 2 lines, but it really doesn't have a symbol for whole numbers. Because if we're going to talk about 0, we're also talking about negatives. And our negative numbers are actually our integers. So we start adding negative numbers in. So what this means for us now is, well, and as you'd guess, integers does have a symbol. Anybody have a guess what it would be? Almost, it's a Z. Yeah, it doesn't make sense because there's a few that just don't make sense. Integers is a Z. I don't know why they chose Z, but they did. So up to this point, integers gives us negative and positive numbers and 0. Now, the way this works out is that a net integer is a whole number. So a natural number can be a whole number, can be an integer. Because 1 is an integer, yes. It's also a whole number, and it's also a natural number, yes. Negative 2, is that a whole number? But it is an integer, yes. So the natural numbers are a subset of the whole numbers, which are a subset of the integers. Is that starting to look like a number line? Yes? What are we missing? Some of the stuff between the numbers, yes? And that would be our rational numbers, anything we can write as a fraction. Now, our rational numbers is going to be a, let's see if I remember this right, Q. So the symbol for rational numbers is a Q with a line. Integers was a Z, W, and N. So rational numbers are some of our decimals. So anything we can write as a fraction. If you can write it as a fraction, it is a rational number. Well, rational is, well, the first half of it is ratio. Ratio is a fraction. So if we can write it as a fraction, it is a rational number. Any questions on any of this so far? We good? Can we always write numbers as fractions? Are there any numbers that we cannot write as a fraction? Pi. The next one is phi, and then we have e. You won't deal with phi at all. E will come up in this class. Pi you've already dealt with, yes? Well, also we have the square root of 2 is a non-repeating, non-terminating decimal. These are irrational numbers. So again, this is really, all this is doing is filling in that number line. Because these are numbers that lie on the number line, but just don't, we can't write them as a fraction. So we call them irrational. And our irrational numbers is our I with 2 lines. Irrational is the I with 2 lines. And there's one more type. Do you have an idea what the next one is? Real numbers. Because you've at least heard of that by this point where we talked about the set of all real numbers. So any of these here, all of these are defined to be real numbers. We'll talk about imaginary numbers later on in the year. Because there are such things as imaginary numbers. And you guys deal with them every single day. Is that kind of surprising? That you would deal with or kind of come into context with where imaginary numbers would come into play? A little bit, maybe? Don't think so? Kind of hard to imagine where that would come into play. All right, well, how many of you own a cell phone? Every single one of you. You deal with imaginary numbers. Because if the cell phone is completely powered off, there's no power running through it, does it still have the potential for electricity to run through it? Yes. How can we mathematically quantify something that isn't currently running but still has the ability to run? That's where imaginary numbers come into play, because they allow us to be able to quantify something that's not happening now but can happen later. And then where it's come into play, and it comes into electronics everywhere. It's all across electronics. Anything that deals with electronics or electricity has imaginary numbers in it. And we'll cover some stuff with imaginary numbers at a later date. So any questions on this here, these different number types? No? We're good with this here? Because they come into play when we start trying to define things like writing sets and subsets. So, like this here, the whole numbers 50 through 54. If we want to write this, writing this set or subset in set builder notation, well, what can we do? Well, I can do a bracket 50, 52, 54. There's 5 of them. I just listed them because that is the set containing 50 through 54, and they're all whole numbers, yes? Because with whole numbers, it's just counting. We don't have to deal with decimals or fractions or anything else in between each number. We're just talking about 50, 51, 52, 53, and 54, yes? Now at the start, I talked about the set builder where we saw the bracket and the lines, X, such that we can write it that way also. Because what we would do is the set of X, that is an element of the whole numbers, because we said the whole numbers. So we're defining it by X being a part of the whole numbers, such that 50 is less than or equal to X is less than or equal to 54. This is another way to write it. Now, me and I would agree, the one on top is easier to write, isn't it? Because there's only, how many of them? 5. I can list all 5, yes? But it's not always going to be the case that is easily listable. The real numbers between 0 and 4. Okay, can someone give me a real number between 0 and 4? 1. How about another one? Okay, another. 2.5, 3.5, 4.5, 0.11, 0.111, 0.1111. We can come up with an infinitely number of numbers between 0 and 4. Actually, let me take that back. I can come up with an infinite amount of numbers between 0 and 1. It's actually very easy to come up with that. Let's think about starting at 0. We can go off to infinity, yes? So that's easy to understand. Well, between 0 and 1, what I can do is go 1 over 1, 1 over 2, and I could just put that number in the bottom of a fraction, yes? There's an infinite number. Well, then I can do 2 over 3 and go that way an infinite amount of times. I can do 3 over 4 and keeping 3 on top. And I keep making an infinite number of numbers inside of just 0 and 1. 0 to 4, we can fit a lot between 0 and 4. So being able to list it out like we did with the last one, which was pretty easy, this here, that's a challenge, isn't it? Because we can't list them all. So this is where set builder notation comes into play. Because here, what we have is the set of all real numbers. So if there's nothing there, we call this here the set of all real numbers. Now, the other way we can write is the set of x. We say for all x is an element of the real numbers, such that what? It's 0 to 4, yes? So 0 is less than or equal to x is less than or equal to 4. The set of all x, the set of x in the real number such that x, 0 is less than or equal to x is less than or equal to 4. So we've described this here mathematically. And not always it's going to look nice, but sometimes it does. Now, as I was just saying a minute ago, we don't have to do this always. If we're talking about the real numbers, it's almost understood to be the real numbers, to where we could rewrite this as the set of all real numbers x such that x, this here. Questions on this here? We go with this here. This is where we do have to be specific, because it's not talking about real numbers, it's talking about what? Integers. So this here would actually be easier to write than the last one. I mean, barely. But we'd still have to have over 200 numbers to write out. I wouldn't want to write that 200 times. So we would still stick with x is an element of what? The integers. Such that negative 100 is less than or equal to x is less than or equal to 100. So the first part defines our set because we're talking about integers. So we're saying x is an element of the integers. X, the values of x are integers. And it's from negative 100 to 100. And that's it. Questions on this here? We good with this here? We're going to do one more. We're not doing prime numbers. Let's see here. Set of numbers except for negative 6. The set of all real numbers except for negative 6. So that means any number except for negative 6 is going to work. There's several different ways we can write this. I'm going to say the set of x is an element of the real number such that negative infinity is less than x is less than negative 6. And negative 6 is less than x is less than infinity. Because we're essentially quantifying it to include all the numbers. And if you want to wait for a minute and pick which one you like best, you can, because there's like 5 different ones I'm going to do here. Because Stormy's probably going to say there's an easier way to write this. You ready? Because it's all real numbers, right? Because that's a lot simpler, isn't it? Well, not a whole lot. We just dropped two things. But if I say x is an element of the real numbers, we're talking about pretty much all of them, yes? If it's a real number, it's all of them. But what are we saying? Except for we're excluding one, right? We can do it that way. You know, because we could also, I mean, talking about kind of more upper level math type stuff, is we could do interval notation. And this upside down U is the union. We're talking about the two together. So there's many different ways to write this stuff, many different symbols. And a lot of the time we're using these symbols to be able to make it so that it's easier and simpler to write. On a whole, mathematicians are very, I would say, lazy, because if they don't have to do something or they can do it simpler, they're going to do it simpler if it's possible. Let's see here. And what we're going to pick up tomorrow, and we're going to start off with, is with our interval notation. And we're going to finish that up tomorrow.